Hey, welcome to Unit 2. I am Mr. Sullivan, this bald man right here who is extremely scared. The reason I'm extremely scared is I'm with these other Algebros. Just wanted to give you a picture of who we are. I know you hear our voices quite a bit. So this is me. I'm doing Unit 2. This is Mr. Bruss. He teaches at Ramstein High School in Germany. He did Unit 1. You heard him. Great job, Mr. Bruss. Mr. Kelly teaches at Kaiserslautern High School with me. He's going to be doing some units later. And Mr. Bean also is at Ramstein High School, and he'll be doing, I believe he does Unit 3. A couple of things you need to know about these guys. These are great teachers, all right? Mr. Kelly won a presidential award for teaching. He's an outstanding teacher. Mr. Bean followed in his footsteps a few years later. He won a presidential award for teaching. Great teacher. Mr. Brust here, then he was the district teacher of the year right shortly after that. Another fabulous teacher. And me. I'm also here involved and teaching you. I think I'll do a good job. I'll try my hardest. But I'm riding these guys' coattails, right? They're pretty great. So let's take a look. Today we're going to talk about true and false statements. The great thing about being true or false is it's really hard to be true all the time, right? As a kid, when your parents catch you in a lie, it's because you are not 100% true. And if you're not 100% true, you're basically lying. So let's take a look at this statement here. Mr. Brust is always fashionable. Well, yeah, I mean, you look around here. Well, look at this guy. Bow tie. Not many people can get this look off, but he is very fashionable in this picture. The vest, the bow tie, what a job, right? Then over here, they got the opposite spectrum. I have no idea what he's wearing here. He may have taken this out of his wife's closet. I'm not sure. But some people would say that's fashionable, but I don't think this is. I don't know what he's wearing. I believe these are female glasses, which is fine. I don't care. But he's not pulling it off because of this mustache. All right, that's a mustache from the 1980s, and we are in 2000, almost 20 now, getting into those times. So you have to keep track. That is not fashionable at all. All right, so is this statement true? Well, it's true some of the time, but since it's not true all of the time, then it's definitely not true. So it would be false. All right, so how about the statement 2 times 2 plus 5 equals 3 times 4 minus 3? Is this true or false? Remember, for it to be true, it's got to be true all the time. Let's take a look. 2 times 2 is 4 plus 5. And then over here we have 3 times 4 is 12 minus 3. So we have 9 equals 9. Well, that appears that is the exact same thing, so this is definitely true, right? And I apologize now for my handwriting. It is terrible. Okay, so this is a number statement. We use all numbers, all right? So what you need to do right now is you should pause the video. A lot of kids are always saying, oh, you go too fast. Well, we go fast because you can pause the video, write down information, and then unpause it and listen to what we do, all right? I'm not going to just wait for you to copy this. I need you to actually pause the video. All right, so a number sentence is a statement of equality between two numbers. It is true if both numerical expressions are equivalent. So was 2 times 2 plus 5 the exact same thing as 3 times 4 minus 3? It definitely was the same thing. That's why this number statement is true. So let's determine the truth values of the following ones, right? I want you to take a second and see if these things are true or false. So pause the video real quick and see what you get, all right? So hopefully you pause the video and actually try these, all right? Because you have to remember, you have to be involved in your education. And so when we say pause the video and try these, you need to pause the video and try these. It's important for you to see how you are doing before we show you how to do everything, all right? We're not going to let you move on just because you watch the video. You actually have to learn in our class, so take the time and try it. All right, let's take a look here. So the first one, all right, number 1, I made common denominators here, so I multiplied this by 5. So now I have 5 over 10, plus I multiplied this by 2, 8 over 10, which is 13 over 10, and I changed that, I divided it, got a decimal of 1.3. And that was the same decimal as 2.05 minus 0.75. Since they're the same, it is definitely true. All right. Number 2, this looks like it should be true. 25 minus 16, that's 9. The square root of 25 is 5, the square root of 16 is 4, but 5 minus 4 is 1, and the square root of 9 is 3. And since these are not the same thing, even though they look like they're the same thing here, it is false. Number 3, a lot of kids think this is true before they actually work it out. It makes sense, right? I have an exponent of 2, an exponent of 3, and it should equal an exponent of 5. But that's not how exponents work. 4 squared is 16, plus 4 to the third is 64, and that is 80, and 4 to the fifth is 1024. So since those are not the same, again, it is false. So now the question is, can any of these be both true and false? Well, we've kind of talked about this, right? You're either true or you're false. These are numbers. Numbers don't change, all right? And since the numbers don't change, there's only one way to make it true, and then the rest will be false. But there are times where there could be both true and false. All right, so pause the video and write down what it means to be an algebraic equation real quick. So an algebraic equation is a statement of equality between two expressions. So maybe we have 2 plus 4 and it equals 2x plus 1. One expression here and another expression here. They can be number sentences like 2 plus 4. They're just solely numbers, so they're number sentences, but they often contain symbols whose values have not yet been determined. Those are variables, right? And what's the number one variable we often use? We often use x as a variable. Now you can pretty much use any symbol you want. You know, stay away from O because it looks like a 0 or L because it looks like a 1. But it stands for something. And this is how we can have sometimes it's true and sometimes it's false. See, I could put maybe a value of x in here that makes this true, and I could put a different value in that makes it false. So here we have 3 examples, and I want to take a look at each of them. Now, the question is down here. Which of these values makes these algebraic equations true? So we're given some values. We want to see which one makes it true. So let's plug it in. I'm going to do the first one by hand, and then you'll see negative 6 over 3 plus 2. Does that equal 6? Negative 6 divided by 3 is negative 2 plus 2. That's 0. So it's definitely not negative 6. Try negative 3. Negative 3 divided by 3 is negative 1. Negative 1 plus 2 is not 6. That's not it. 0 divided by 3 is 0. 0 plus 2 is not 6. Ooh. 3 divided by 3 is 1. 1 plus 2 is not 6. And 12 divided by 3 is 4. 4 plus 2 is 6. So for this case, our only one that would work is 12. Let's try the next one. Erase this. All right, now we have x plus 1 times x plus 2. So negative 6 plus 1 and negative 6 plus 2. Negative 6 plus 1 is negative 5. Negative 6 plus 2 is negative 4. And a negative times a negative is, in fact, 20. So negative 6 works. But we got to try them because there might be more. That's why there's that s there, right? Negative 3 plus 1 is negative 2. Negative 3 plus 2 is negative 1. Nope, that's not going to work. 0 plus 1 is 1. 0 plus 2 is 2. Nope, that's not going to work. Let's try the next one. 3. 3 plus 1 is 4. 3 plus 2 is 5. 4 times 5 is 20, so that works. Plug in 12. 12 plus 1 is 13. And then 12 plus 2 is 14. Oh, that's way bigger than 20, so that doesn't work. So in this case, we have negative 6 and 3. We have 2 values there. Interesting. All right, let's try the next one here. Let's erase these and start over. Oh, come on. Let's erase these, won't you? There we go. All right, so here we go. What number is squared? That means times itself equals negative 4. So negative 6 times negative 6 is positive 36. So that's not it. Negative 3 times negative 3 is positive 9. So that's not it. 0 times 0 is 0. So that's not it. 3 times 3 is 9. So that's not it. And 12 times 12 is 144. That's not it. In fact, none of them work in this case, right? Is there any number that you know of that'll work for this? Any number squared? I know a lot of people are thinking 2 maybe. 2 times 2 is positive 4, maybe negative 2. A negative times a negative is a positive. See, in this case, there will be no number. There is no number that when you multiply it by itself will equal negative 4. All right? All right, let's take a second, pause the video, write down what a solution set is. All right? So a solution set is a set of all values to a given variable to make the equation true. So when we went back, anytime the number we put in for the variable made it true, that was our solution set. These are the solutions to the equation. When solving an equation, you find the solution set. Very good. So let's find and describe the solution set. So verbally, we want to know what number I can take the absolute value of and it comes out 6. Well, what number can I take an absolute value of and it comes out 6? Let's think about this. Well, the absolute value of 6 is definitely 6, right? Because absolute value takes whatever the sign of that is and makes it positive. So what other number? Negative 6. The absolute value of negative 6 is 6. So if we were to talk about this verbally, we may say the 6 and negative 6 are solutions. All right? How would it look graphically? Let's draw a little number line here. And I'm going to have negative 6 here, 0 and 6. Now you could put every tick mark if you want. All right? And I'm going to have a little dot at 6 and negative 6. All right? Set notation. Set notation's pretty fancy. Why is it fancy? Well, you have to use these fancy brackets. That's the first thing. All right? So I'm going to put all my possible things in here that are my solutions. So let's see. Negative 6 is a possibility, right? And I put negative 6 first because it's the smallest one on my graph. Then my other possible solution is 6. And I'm going to end it with one of those fancy brackets. All right, let's go over here. What could I put in this one to make the absolute value of h come out to be a negative 6? Well, remember, by definition, this is a distance to 0, and it's always going to come out positive. Is there any number I can put in here that comes out negative? No. There is no solution would be a good verbal, right? Graphically, what would it look like? Well, let's draw a line here. Let's say I got negative 1 here. I got 0, and I got 1. Or am I going to put anything on that graph? No. Why would I? I have no solutions. Let's do set notation. All right, let's start with my fancy bracket. Boom. Put my other fancy bracket in here. Now let's put every single thing in here that's a solution. Well, we're done because there's no solution. So that would be how I would write it in terms of a solution set. Okay? So let's talk about set notation for a second. All right, like I said, these brackets indicate a set which is a collection of numbers. All right, and these numbers are just called elements. That's our fancy word. We're going to list the elements in increase in order. All right, so for example, negative 6 and 6. We didn't put 6 and then negative 6. The set can be empty, right? If we have no solution, the set can be empty, and we call it the empty set. And sometimes we're going to have to use a description of sets. So for example, if you notice here, when I say x is greater than 4, well, 5 is greater than 4, 6 is greater than 4, 7 is greater than 4, 8 is greater than 4. I can't write everything out, but so I have to write x is greater than 4, and I also have to delineate here and say, only talking about my real numbers right now, okay? So I'd say, here's a description of my set I'm in, and spoiler alert, it's really only going to happen when I'm in the real numbers for right now, okay? And then I would put my descriptor. So let's take a look over here. Describe the solution set for this one. X minus 3 over x minus 3 equals 1. So over the set of positive real numbers. All right, here we go. So what number can I put in for x that when I subtract 3 on top and bottom it equals 1? So 0, 0, imagine we put in 0. 0 minus 3 is negative 3. 0 minus 3 is negative 3. Negative 3 divided by negative 3 is 1. 12 minus 3 is 9. 12 minus 3 is 9. 9 over 9 is 1. Are we getting in here? Any number I put in here, right? So any real number will work for this. is a solution. All right, so let's talk about graphically. Let's draw our graphic. Let's draw our number line 0. I'm just going to put a 5 over here, -5. So how would I any of these numbers work, right? Any of these numbers. So I'm going to make it big and thick so you guys can obviously tell. So that means any of these numbers here work. And any of these numbers I haven't listed, so I need to have these arrows on the end, right? And I know that kind of, got in the way, but sorry. Deal with it. All right, set notation. The first thing we need is our fancy brackets. So our fancy brackets. So now let's put in all our answers. Holy cow. How can I put all our answers in here? Well, you could simply write, all real numbers in here if you'd like. That's great. Or what was the other way we talked about? Writing it out like that, all real numbers. Okay? Either one of those will work. All right, so look here. We want to solve for g, so we want to find our solution set to when does 2g plus g squared equals g times g plus 2. All right, so the first thing, remember, I try to simplify. So 2g plus g squared equals, I'm going to multiply g times g is g squared. G times 2 is 2g. All right, now I'm going to use the commutative property here and just move these around. So now this is 2g plus g squared. And the reason I did that is very simple. What do you happen to notice? This is the exact same thing as that, right? And what does that mean? When they're exactly the same thing, it doesn't matter what I put in for g, right? As long as I have a real number, it's going to work. So verbally, all real numbers. That would be our verbal solution. How about set notation? Again, we talked about this. We could put that in the set, all real numbers. Or we could have just denoted it like such, right? All right, graphically. Yeah, I know this one is kind of boring. It's very similar to the last one. So graphically, it is everything on our number line, right? All numbers. And make sure we denote that left and right. All right, so I want you to pause the video and try this one on your own. Okay? All right, let's take a look. So again, I'm gonna add 5 over here. That makes sense to me. So p is less than -2. So in other words, what makes this true is any number that's less than -2, right? So -2, let's see, -2 is -2 less than -2? No, but -3. So any number less than -2. So any number less than -2. Set notation. All right, now let's check this out. Is it possible for me to write every single number that's less than -2? No. And since I cannot write every single number, I have to delineate that we are in the real numbers. So not x this time. See, we use x so much, I just get used to it. P, so whatever my P is, it's a real number. Then I'm going to tell me what is my conditions for that. So it's such that P is less than -2. So some of you might be asking, when do I know I have to put this in and when don't I? When you cannot possibly write all the numbers. So for example, maybe we had 4, 6, and 8 made it true and that's it. I could write those out. Good. I cannot write every possible number here, so that's why I had to do it that way. So let's look at it graphically. So I'm going to start at 0 here, -1, -2, -3. So I want all the numbers less than -2. So you have to remember, I'm going to start at -2. I'm going to have an open dot because it's not going to be included. And I want all the numbers less than that. So all the numbers less than that are this way. All right? So that would be my graphic representation. Okay? All right, I threw a lot of information at you. I totally understand that. The sooner you start to learn it, the better off you're going to be. I want to leave you with a quote. Failure is part of the process of success. A lot of our kids, they just try to rush through everything. They just want to get and take that mastery check, and they think they'll learn it on the mastery check. You don't have to do that. That takes you longer. Right now, the process of failure takes place. You're going to go start your practice right now. If you copy our answers, you are not failing. You are copying. And since you're not failing and learning from your mistakes, you are not going to be successful on that mastery check. So go and start your problems. As soon as you get stuck, ask for help right away. Don't wait. Ask as soon as you can. As soon as we can help you figure out what your mistake is, your failure becomes your success. And that's what we want. We want and believe you can all be successful. So go out there and, fail with your head up high, all right? Have a great day. See you later.